Okay.
Leap's too close.
Sorry?
The leap is within arm's distance.
I know.
Treat the camera better than you would treat Pat.
The camera would want me to have it.
Okay. So,
Actually can't see it.
so I want to do a bunch of things with the Riemann zeta function today. And so this will be the lone day for analytic number theory. If people are interested, one of the possible classes next year is a class in analytic number theory. If you are interested, let me know. If you are a junior or lower. So it's the sum n goes from 1 to infinity, 1 over n to the s. It's a product. P is prime. 1 over 1 minus p to the s. Inverse. Real part of s is greater than 1. It's going to turn out that the behavior of this function will tell us everything we want to know about the primes. The difficulty is extracting that information. The other issue is, this is only defined if the real part of s is greater than 1. So how can we make sense of this for all values of s? Analytically. So we've talked about the analytic continuation. What's the one place where the function blows up? Where's its one pole? Not at 0. At s equals 1. So it has a simple pole of residue 1 at s equals 1. The big question is, where are the zeros? So it turns out it has zeros at s equals negative 2n, n greater than or equal to 1, an integer. So at the negative even integers, it has a 0. We give this a very obvious name, the trivial zeros. These are called the trivial zeros because we understand the negative even integers quite well. And in fact, they have very little effect in terms of the behavior of the Riemann zeta function. These are really coming from the gamma factor in the functional equation. So we looked at the completed zeta function. It was pi to the minus s halves, gamma of s halves times zeta of s. Well, gamma of s halves, the gamma function blows up at the negative integers. So gamma of the s halves will blow up at the negative even integers, so the zeta function has zeros to compensate for the poles of the gamma function. The other question is, where are the rest of the zeros? So in fact, zeta of s does not equal 0 if the real part of s is greater than or equal to 1. Greater than 1 is easy. Equal to 1 is moderate. There's a clever idea. And so I'm probably not going to go into the details of how you prove it when the real part of s equals 1. But it's very important to show that there's no 0 with real part 1. And there's a really nice trig identity that's used. So it's a nice trig proof. Then, what is left? All the other zeros are between 0 and 1 for their real part. And the Riemann hypothesis all non-trivial zeros have real part equal to 1/2. So in some sense it's saying that the zeros are distributed as symmetrically as possible. So when you look at the functional equation, we relate the values at s to the values at 1 minus s. So if we can understand the values from 1/2 onward, we understand what's going on from 1/2 below. So if there's a 0 at 1/4, there's a 0 at 3/4, and vice versa. So we only have to study for the real part of s greater than or equal to 1/2. And in Riemann's paper, it's a beautiful aside. It would be nice if the zeros were distributed as symmetrically as possible. That's not really relevant to what I'm doing today, so I'm going to just move on. It turns out Riemann actually calculated the first 6 zeros of the Riemann zeta function and didn't tell anybody. It was only discovered about 7 decades later when a prominent mathematician, Siegel, was going through the archives and going to Riemann's university and found papers by Riemann. And if you've ever seen papers where you've worked on a problem, then you work on another problem, you kind of turn the paper around and you see, where do I have free space? It's a very interesting, exercise Riemann's got the first 6 zeros written down. He actually had a better formula to calculate zeros of the Riemann zeta function than people had been able to find in the intervening 70 years. And that was just, sitting in an attic. One of the ways we calculate the values of the Riemann zeta function, or calculate the zeros of the Riemann zeta function, and this was one of the suggested homework problems, is there's a function related to the Riemann zeta function which is real valued on the real line. And it has the same absolute value as the Riemann zeta function. So it has the same value as the Riemann zeta function in absolute value, and it's real valued. We look for sign changes of this function. And whenever there's a sign change, the intermediate value theorem, since it's continuous, assures us that there was a zero. And so, this whole divide and conquer method is actually one of the most powerful techniques we have to find zeros. All right, what I want to do now is prove zeta of s does not equal 0 if the real part of s is greater than 1. If people are interested, if there's time today, I'll give you a false proof of the Riemann hypothesis, which is worth $1 million. So if you can fix the proof, I will let you keep 95% of it.
Hey.
The federal government will let you keep about 4 or 9. Can somebody give me a type of s whose real part is greater than 1 where it would be easy to prove that the zeta function is not 0 there? Where is it easy? I'm sorry?
Even.
Why is it easy at the even integers?
Because we can find someone with the into even.
Okay, so that's using some heavy machinery. So I agree that it's easy at the even numbers, but it's easy for an easier reason than what you're advancing. Why is it easy to show that zeta of s is not 0 if s is an even number?
Because they're all positive?
Yes. Right? Summing positive numbers, you've just dropped an atomic bomb on the Riemann zeta function, which is fine, and we'll do that later. But all we have to observe is, if s equals sigma is real and sigma is greater than 1, zeta of sigma is a sum of positive numbers, not 0. Right? Okay, so it's not a problem if zeta is evaluated at a positive real number greater than 1. The difficulty is, well, what if we evaluate it at a complex, at s equals sigma plus it, where t is not 0? The difficulty is now, maybe we have some cancellation. If you look at the series expansion, now I have signed quantities and maybe things can cancel. So there are two ways to attack. We could use the sum, and we can use the product. Which do you think is easier to show something is non-zero, the sum or the product?
The product?
Product. Why?
Because we just show there's no number that is 0.
So one thing is to show that there is no number that is 0. Now, of course, if the numbers are decaying, the product could tend to 0. So we have to make sure that the product isn't decaying too fast. But that's a lot better for me than trying to evaluate the sum and deal with all the oscillation. So let's study the product. Let s equal sigma plus it. Sigma is greater than 1. T is an I. T might be 0, in which case it reduces to what we already studied. So zeta of s is the product over p, 1 minus 1 over p to the sigma, 1 over p to the it. And I want to try to understand how big can this be, how small can this be. Which am I more concerned with, upper bounds or lower bounds?
Lower bounds.
Lower bounds. I'll do both because it's fun, but I really care more about lower bounds. So if I look at the absolute value of zeta of s, can you give me an upper bound? So the difficulty is I have this p to the it factor. What value, for a specific choice of p, what value of t will make this whole thing as large as possible? Remember, I've got a minus 1. What value do I want 1 over pit to be? I'm sorry? I think you want the opposite. I think you want negative 1 later. So instead of negative 1, what do you want?
Just
Positive 1.
Positive 1. If this is positive 1, I'm subtracting as much as I can from 1. I'm making the denominator as small as possible. And then its reciprocal will be as large as possible. This is less than or equal to the product over p of 1 minus 1 over p to the sigma inverse. Oh, well, what is that equal to?
oh, that's the
Just the
first
case
case.
before.
Yeah.
Yeah, but and this is just zeta of sigma.
Right.
So this is an easy bound to get, and it's a completely useless bound. Oh, gee, I have a sum with oscillation. I remove the oscillation, and it's no larger than the sum without oscillation. You know, that's not going to help us at all, but it's a nice note. The other direction, what I want to do is, the worst case would be if 1 over p to the it is equal to negative 1 every single time. That'd be the smallest possible. So we'd have the product over p of 1 plus 1 over p to the sigma inverse. And so I now need to just make sure that this isn't too small. There's a really nice trick we can do. The Riemann zeta function does not have 1 pluses, it has 1 minuses. How can I get a 1 minus from a 1 plus?
You could add and subtract 1. No, it doesn't.
Okay, but do that on a log scale.
Oh,
Well, first of all, we don't want to add and subtract 1.
right, now.
You want to use a word other than add.
Yeah.
You want to
Multiply.
multiply by 1. So how can I multiply by 1?
Isn't it 1 minus
Yeah,
1?
yes. So look at the product over p, 1 minus 1 over p to the sigma inverse, times the product over p of 1 plus 1 over p to the sigma inverse, divided by the product over p of 1 minus 1 over p to the sigma inverse.
Wait, that's not what I meant. But
Oh, what did you mean? What did you mean?
never mind. It's fine.
Okay.
It's not fun.
This is the way I want to multiply by 1.
Okay.
And as somebody
Can you
with...
explain what you were... Oh, okay.
So this is 1.
Yeah, yeah.
Okay, the Vanna White day continues. Why do I want to do this? Well, if I take 1 minus and 1 plus, what happens when I multiply them together?
Magic.
Magic, yes. Magic in what sense? What do we get?
Cancellation.
Cross terms go away.
The cross terms go away, and we get the product over p, 1 minus 1 over p to the 2 sigma inverse, divided by the product over p of 1 minus 1 over p to the sigma inverse. What does the numerator equal?
The base. 2 times.
Yes.
Yeah.
Zeta of 2 sigma, and the denominator? Zeta of sigma.
No, 1 sigma.
And that will be less than or equal to the absolute value of zeta of x. And there's our lower bound. So this is an extremely useful trick. It's a really nice way of multiplying by 1. And so I thought, there's a limit to how much number theory we can get into. This was an idea that I've used in several of my research papers to simplify expressions and make them far more tractable. And by multiplying like this, I've now reduced myself back to a place where I understand things. I understand products of 1 minus. I don't understand products of 1 plus. Yes?
No, never mind.
Okay. Was your answer with an M&M or?
No.
Okay. I appreciate your honesty. I'm not quite sure if my kids are at that level yet. Alright. Proof of the prime number theorem. Nice. Okay. So let's see how much time we have. Okay. So I think I've mentioned in the past that people had conjectured various forms of the prime number theorem for a while, and eventually we stabilized around pi of x, which is the number of prime primes p less than or equal to x should be about x over log x. A better estimate is actually the logarithmic integral, which is the integral from 2 to x of dt over log t. And the first term in the expansion of that is actually x over log x. One of the suggested problems is to actually just calculate a few terms of this approximation. This does a little bit better job than x over log x. It just picks up some of the error terms. The Riemann hypothesis is essentially equivalent to Li of x minus pi of x is less than or equal to x to the 1/2 log squared of x. So one way of understanding the Riemann hypothesis is it's just a statement about up to some constant. It's just the difference between pi of x and our approximation is like square root. And in fact, one way to provide some justification for this bound is to do things probabilistically. Is flip a coin and declare the number n to be prime with probability 1 over log n. And if you do this, there's a name for this theorem in probability. So you want to count, how many primes you expect to have and compare it to your prediction. And then the fluctuations are significantly smaller. It's the central limit there. That if you have n observations, the variance is often like square root of n. So the log factors are a little bit interesting, but essentially this is the central limit there. If I give you a random sequence of primes, now again, what does random sequence of primes mean? The primes are 2, 3, 5, 7, depending on whether or not you're an engineer, 9 or 11 is next. There's only one sequence of primes. There's no such thing as a probable prime. Well, what we can do is we can try to consider other sequences of numbers that have similar properties as the primes, and then ask what other properties do they have. So the twin prime conjecture says that there are infinitely many primes that differ by 2. If I do this random flip model, do I expect with probability 1 there to be infinitely many twin primes? We believe every even number can be written as the sum of 2 primes. If I do this, do I expect this to be true? You can build a lot of intuition for the actual primes by looking at these random sequences. But not always. There are some special things that happen for the primes that don't happen for any other sequence of random primes. The biggest is unique factorization. Every integer can be factored uniquely as a product of prime powers. If you have random primes, you don't have something like that. You don't have this Euler product that you have in the Riemann zeta function, where zeta is the product over primes. So there are some differences between the actual primes and these random primes. And of course, whenever you do things with probability and stuff like this, you get, for almost all sequences of random primes, this should be true. Great, it's true for almost all sequences of random primes. Is it true for the one sequence of random primes that I happen to care about, the actual primes? And so that you will not get information about. Okay? So this is one way of interpreting the statement of the Riemann hypothesis. It's a statement about how good our estimate on the number of primes is to the number of primes. Another way to interpret the Riemann hypothesis, as I said before, was the location of the non-trivial zeros of the Riemann zeta function. And it turns out these two things are related. The error term in counting primes is related to the number of zeros and the location of the zeros of the Riemann zeta function. When people were first trying to prove the prime number theorem, it took, say, around 50 years, from the 1840s to the 1890s, before we finally got a proof. And the proof, Riemann's paper was, I think, 1849 or 59. I think it was 1859. The proofs all heavily used complex analysis. And a lot of complex analysis was developed precisely to attack the prime number theorem and other problems like this. And people found this very upsetting that this was the proof we got of the prime number theorem. We're counting integers, and we have to resort to contour integrals and square roots of -1. For the quantum mechanics people in the classroom, this is probably not that big of a deal to you now. But at the time, having to shift to the complex plane to count integers just seemed wrong. And so there was a search for an elementary proof of the prime number theorem. We do have one now. For a long time, people felt no such proof would exist because we've been looking for it for so long and no one was able to find it. They finally found it, and the proof is much worse than the complex analysis proof. Not in terms of difficulty, but in terms of the estimate it gives for the error term. So as long as we have something that's smaller than x over log x, we win. And we show, okay, the main term of pi of x is x over log x. The elementary proofs give much weaker results than complex analysis. It's not surprising because they're not using as heavy machinery. So what I want to do is I want to sketch how we would attack the prime number theorem using complex analysis. I don't want to do all the integrals. I want to just kind of show you what goes on. And so we've talked a little bit about this before. So zeta of s is the product over p of 1 minus p to the minus s inverse. And again, whenever we see a product, we have been trained to immediately take the logarithm. So we get the log of zeta of s is the sum over p. We have a minus sign that comes out, the log of 1 minus p to the minus s. But in complex analysis, what do you like to integrate? If I give you a function, what's a really nice function to integrate related to your original function?
The derivative of the function.
The derivative of the function. That's actually the logarithmic derivative. F prime over f is the derivative of log f. If we take the derivative of log of zeta, we get 1 over zeta times zeta prime. So we get zeta prime of s over zeta of s. All right, now we take the derivative, so we'll have negative sum over p, 1 minus p to the minus s. Now we've got to take the derivative of the top. P to the minus s is e to the minus s log p. So we get a log p coming down, p to the minus s, and then we have two negative signs. So this is the formula for zeta prime of s over zeta of s. Okay. If the numerator wasn't there, it would just be a geometric series. And so what we can do now is we can use the geometric series formula and get zeta prime of s over zeta of s is going to be negative the sum over p of log p over p to the s plus the sum over p log p over p to the 2s, etc., etc., etc. And this is just from expanding the denominator 1 minus p to the minus s. Normally when you expand 1 over 1 minus r, it goes 1 plus r squared. Why am I not starting with 1? Why am I starting with 1 over p to the s? Because we have this extra p to the minus s in the numerator. Alright, so all of this stuff turns out to be a nice function or a good function. And I'm going to completely ignore it from now on. That's one approach. The other approach is to look at a related function and say that this is negative the sum over n of lambda of n over n to the s, where lambda of n is the log of p, if n equals p to the k, p is prime, and 0 otherwise. So what you're going to get today is you're going to get a sense of how analytic number theorists think. We're basically accountants. And we keep track of the main terms and the lower order terms. This function here, I'm summing over all the integers of lambda of n. So lambda of n is just log of p if my integer is a power of a prime and 0 otherwise. Oh, okay, well good. So if n is a prime, I get this. If n is p squared, I get this. If n is p cubed, I get the next term. So this is a way to just deal with everything all at once. And then I don't have to worry about just throwing things away. What I'm hoping you're getting a sense of is that it's much easier to discriminate. And we've talked about this before. You don't want to count all primes equally. You want to weight each prime by the log of it. And the reason is the natural quantity to study is the Riemann zeta function, or its logarithmic derivative. And when you do that, it introduces log weights. So what you do is you just work with the log weights and then you remove them. So the idea is if you understand either the sum of log p less than or equal to x, or the sum n less than or equal to x of lambda of n, you understand the sum of 1 over p less than equal to x. So I really only have to understand one of those three sums to understand the other two. So what I want to talk a little bit now is, why is it enough to understand one of these sums and get the rest? Which sum would you like to know? At the end of the day, which do you care about? The last one. We care about how many primes are at most x. I don't care about how many weighted primes are there. I want to count how many primes there are. These ones are just technically easier to study. And once we study these, then we deduce information about them and we propagate that and we pass it down to the last sum. So I'll show these two sums are similar. Which sum is larger? The first sum or the second sum? Second sum, right? Second sum contains the first sum. So the sum of n less than or equal to x of lambda of n is the sum p less than or equal to x of log p. And now let's look and see what else we have. Then we have the sum p squared less than or equal to x log p plus the sum p cubed less than or equal to x log p. And now we just want to get a sense of how large is everything else. Well, if p squared is less than or equal to x, how could I rewrite this?
P less than or equal to square root of x?
Yeah, I could replace this as, this is p less than or equal to square root of x. This would be p less than or equal to x to the third. And this would be p less than or equal to x to the 1 over k. And the question is, how large can k be? So can anybody tell me how many terms I could take? Give me a reasonable bound. Is k going to be less than x? Yes.
Log x.
Essentially log x. It's not, can you do a little bit better than log x? Got to be a little bit careful. Log x is technically wrong.
Log x?
Log x base p, or the log of x divided by the log of p. If p equals 2, then that's a little bit higher than the log of x, because the log of x is coming from base e. So, in some sense, the largest value for k occurs when I take p equals 2. And then I would get 2 to the k equals x, so k log 2 is log x, so k is, at most, the log of x base 2. So k is less than or equal to the log of x base 2. And I don't want my bound on k to depend on which prime I'm looking at. I want something that I can use uniformly. And again, this is a big thing for analysts. We love this word uniform. We like to be able to tackle everything all at once. Alright, so now when I'm trying to understand the sum, I've got the sum p less than or equal to x of log of p. Now, how big could this sum be? So what I'll do is I'll take my sum up to x, and I'll subtract, and I'll see how much of a difference can I get between these two. So how big could this sum be? Worst case. Okay, time's up. I heard a beep. How many terms do I have? Well, I need to know the prime number theorem to know how many terms I have.
Yes.
Alright, so let's be crude in the mathematical sense.
You have less than the first sum?
I have less than the first one, but give me an upper bound for how many terms I have. How many primes are there at most square root of x?
Square root of x.
Square root of x. Could you do better and do maybe square root of x over 2? Sure, we don't need to. And how big is each log p?
Log x.
Log x. You could do a little bit better and say log square root of x, but it's not going to help us. The next term is at most x to the 1/3 log x plus x to the 1 over k log x. But how many terms are there?
K minus 1. Oh.
This is k minus 1, and k is log of x base 2. So this is going to be less than or equal to x to the half log of x log base 2 of x. So that gives me a really good understanding of how much these sums differ by. The difference is going to be at most essentially square root of x with a couple of logs, along for the ride. I could do a little bit better if I really needed to. I could take this term by itself and then just look at all of these terms over here. And if I do that, I'd still have an x to the 1/2 log x from here, but now I have an x to the 1/3 from every remaining time. And I have log x terms. And so I would get a slightly better error estimate with very little work. So the whole point is, if I understand the sum of log p, I understand the sum of lambda p. There's really no difference between the two. Or there is a difference, but the difference is so small, it's not going to really play a role. The M&M still hasn't fallen off. Interesting. You don't have to go for the M&M. Okay? So now, we agree that the first two sums are basically the same. I want to compare the first sum or the second sum to the third sum. I'm not going to do all the comparisons, I'll just do a little bit. Let's look at the sum p less than or equal to x of log p. Can somebody give me an upper bound for that? So the problem is I've got this log x term that's varying. What can I replace all the log p's by?
Log x.
Log x. So this would be less than or equal to log x times the sum p less than or equal to 1. Oh, sorry, p less than or equal to x of 1. And so if we can show this sum is of size x, we would then get x over log x is less than or equal to the sum p less than or equal to x of 1. So if we can show that this sum is of size x, then we have a nice lower bound for the sum of the primes. We would need to do a little bit of work to get an upper bound. Right? Because the problem is we've made everything larger by replacing all of these with log x. So in the interest of time, I'm not going to go through the argument as to how you would get an upper bound. There is a way to argue along these lines. The book goes through that calculation. And it just completes the cycle of arguments that if we understand one of these three functions, we understand all three of these functions. Another way of saying this is, it's not a big deal to remove the log weights. It may look annoying at first that we have to deal with them, but it allows us to use tools from contour integration, from complex analysis, without really worrying too much. Okay, so now it's time for the proof. We'll assume zeta of s does not equal 0 if the real part of s is greater than or equal to 1. So again, we only did it for the real part of s greater than 1. You can read the book for the really clever trig idea, I think it's due to Mertens, to show that it is not equal to 0 if the real part of s equals 1. And it's going to be very important that we do not have any zeros on the line real part of s equals 1. Alright, so how we do this? We've got zeta prime of s over zeta of s, make sure you leave some space, is negative the sum n goes from 1 to infinity, lambda of n over n to the s. Instead of using lambda n over n to the s, we could just do the primes. Do people have a preference between using all the integers and lambda or just using the primes? Good. You shouldn't have a preference, right? Why shouldn't you have a preference? Good, because if we understand one, we understand the both. I either hate them both equally or I love them both equally. I'm indifferent between the two. So since I've already put in this one on the board, let's leave this on the board. Okay, for any of the physicists who are not thrilled about all the time we're spending in number theory, think of how the number theorists felt if there were any in the room when we did all the physics. Okay, payback. Okay? What I can do is I can integrate both sides now. Because it's an equality. It turns out it's convenient to multiply by a factor before I integrate. And then I'll put in a ds. And I'll do some integral. And I'll integrate maybe over the real part of s equals 2. Why might I want to start integrating at the real part of s equals 2?
It's the first integer that's greater than 1.
It's the first prime.
Okay, so we've got first prime, first integer greater than 1.
It's even.
It's even. None of these work. I'll replace 2 with 3 halves to kill all of the reasons against. So it's not...
So we have some wiggle.
Ah, there we go. It's greater than 1. Okay, so why do I care that it's greater than 1?
Because it's.
You want no zeros.
I'm sorry?
You want
So
no
good. So one thing is I don't want to have any zeros on the line of integration. Zeros on the line of integration, poles on the line of integration scare me. That's one reason. There's another reason. It's more basic. What's the first thing you should ask yourself whenever you see a sum? Does it converge? So if I want this sum to converge, I want the real part of s to be greater than 1. So if the real part of s is greater than 1, then I have this expansion for zeta prime over zeta. Okay? And so now, what I want to do is I want to evaluate both sides. Okay, so the physicists who might have zoned out a little bit now, we're back to something that you would love to do.
switch. To the integral.
Switch, right? When in doubt, switch. Right? We have an integral and we have a sum, so clearly this is the same as negative the sum, and it goes from 1 to infinity. We have a lambda of n, then we have an integral over the real part of s equals 3 halves. So if you want, then we have x divided by n to the s divided by s ds. So if you want, think of s as 3 halves plus it. T goes from minus infinity to infinity. This integral turns out to be very easy to evaluate. Or if it's not easy to evaluate, a better way of saying it is, it turns out to have a really nice value depending on n. If n is less than x, the integral is 1. If n is greater than x, the integral is 0. So this is 1 if n is less than x, 0 if n is greater than x.
So, like, yeah, what happened in that point?
So what happens if n equals x? Anybody thinking of going to a career in industry or economics?
No.
Oh, you've got 2 data points, which would be more than enough to extrapolate the entire history. I think 1 is more than enough in a lot of businesses. What would you guess?
1/2.
1/2, and that's the answer. Okay? It's very painful if you actually have n equals x, because now you have the function of 1 to the s. So what you could do is you could just say, let's assume x is not an integer. And if we keep x away from integers, things are a little bit better. Well, if I can count how many primes there are less than 15,000.1, I can count how many primes there are less than or equal to 15,000. So forcing x to be a little bit away from an integer, not a big deal. And then I don't have to worry about that middle case.
I'm really not understanding why, the integral equals 1, 1/2, or 0.
It just, when you roll up your sleeves and do the integration, which I strongly urge you to do, that's what you get. So how would you do this integral? This is, I'm leaving this as a challenge to you. How would you do this integral? What kind of, I mean, does this look like a Calc 1, Calc 2 integral? Calc 3 integral? This looks like a 372 integral. We have an integral over the real part of s equals 3/2. You need to finish the contour. And depending on what n is, you might want to have the contour going like this, where this is 3/2. Or you might want to have the contour going like this, where this is 3/2. And so I will leave this, integration to you as an exercise. Is how would you evaluate that integral? But it should be one of those two contours. And the question is, is there going to be a pole? If so, where is the pole going to be? What will be the residue? And so you can, use the techniques. The Star Wars was on my mind. I almost said something else. You can use the techniques of complex analysis to figure out what the integral is in those two cases. And what's nice is, when the dust settles, we are basically left with negative the sum n less than equal to x of lambda of n, which is basically negative the sum p less than equal to x of log of p. Okay? So we have the quantity we want, right? If we're trying to prove the prime number thing, we want to count how many primes there are up to x. That's basically what we have here. Yes, we have these log weights, but we've all agreed that log weights no longer bother us. We can remove them. All we have to do, and it's a big all, is evaluate this integral. Did I talk a little bit about the Hardy-Littlewood circle method and the integral to describe whether or not an even number is the sum of two primes? Did we do that early in the semester as a motivation? I thought we did.
It was a long time
It was a long time ago. Alright, so if this time I will try to put that in. Just because I write down an integral doesn't mean I can evaluate it. Well, we have an analytic continuation of the Riemann zeta function. What I want to do is I want to start shifting this to the left. So I want to complete my contour. Here's 3/2. And here's a little sketch of the world. Here's 3/2. Here's 1. Here's 0. Here's 1/2. That's the critical line. -2, -4, -6, -8, -10. There are the zeros that the Riemann zeta function has at the negative even numbers. So what I want to do is I want to take my integral and I want to complete it and do a contour. And so I'm going to get contributions from the zeros and poles of the Riemann zeta function. I can also get a contribution from the pole from the 1 over s. And then you can deal with, well, does the Riemann zeta function vanish at s equals 0 or not? Fortunately, it's not going to matter for us. Okay? So when I do the contour integral, if I have a pole, the contribution has a -1 times the residue. If it's a 0, it's a +1 times the residue. Right? That's from the zeta prime over zeta. The zeta function has a pole at s equals 1 of order 1 with residue 1. So when s equals 1, as I move my contour over, I get a contribution. The contribution is going to have a negative sign. The residue of the zeta function is just going to be 1. And then x to the 1 over 1. So I get a contribution of -x. Now I keep moving my contour over. Every time the zeta function has a 0, I get a contribution. The zeta function has no more poles. All that's left are zeros. So I'm going to get plus a sum over the zeros, and we denote the zeros of the zeta function by rho, of x to the rho divided by rho. And now you can begin to see the Riemann hypothesis and the connection. I have a negative here and I have a negative here. I can get rid of the negatives, and I can get the sum, p less than equal to x of log p, is basically the sum n less than equal to x of lambda of n is equal to x minus the sum over rho of x to the rho over rho. So the first thing is, do I have to worry about the contribution from the zeros of the negative even integers? So I'm trying to count how many primes there are. Do I have to worry about the contribution from the negative even numbers? Or are they insignificant next to the power of this main term? What do you think? So what's the first negative even integer? Negative 2. So the contribution is going to be 1 over x squared, and then if I can even get an extra minus 2 in the denominator. Alright, as x gets really large, do I care about a 1 over x squared? No. The next one is x to the minus 4. Do I care about that? Definitely not. In fact, the even numbers, you're going to get the sum of x to the negative 2k divided by 2k. K goes from 1 to infinity. That's insignificant. And in fact, you can even tell me exactly what it is. And there was a negative over here, so I have this. This is just the log of 1 minus, I think x to the minus 2. Just the Taylor series expansion of the log. So I can even explicitly write down the contribution from the trivial zeros. So a similar argument shows a explicit contribution from the non-trivial zeros. That's the difficulty, is we don't know where the non-trivial zeros of the Riemann zeta function is. This is the million-dollar clay problem. You know, where are these zeros? Well, let's think. If I'm trying to calculate what this value is, which is good? Large values of rho, you know, real part close to 1, or small values of rho, real part close to 0. Which would you rather have? The real part of rho close to 1, the real part of rho close to 0. Which is going to be better for your error? 0. Unfortunately, this was a trick question. Because if the Riemann zeta function vanishes at rho, it vanishes at 1 minus rho by the functional equation. So if you have a 0 whose real part is close to 0, you've got a corresponding 0 whose real part is close to 1. What's the best thing that could happen for the error term? I'm sorry? Okay. I set myself up for that one. Nice catch.
It's right there.
Yes. Okay, given the fact that there are zeros, what's the best thing that could happen? On the half line. So the best thing that could happen is if they're all on the half line. Anything close to 0, there's something corresponding close to 1. Anything close to 1, this doesn't matter. If there's something corresponding, it's bad. The best possible case is every 0 of the Riemann zeta function has real part equal to 1/2. And if that's the case, then this term is going to look like a lot of things of size square root of x. Now the problem is I have infinitely many things of size square root of x. But I have a lot of oscillation from the rho, and I have rho and rho bar also being roots. I can do a lot of clever things with the sum to show that the sum converges if you do it in the correct way. I don't really want to go into all the details. I'm hoping that this is enough meat to give you a sense of how the prime number theorem is proved. You know, this is pretty much the details of what's going on. If all the real parts are 1/2, this is like square root of x. And that's the prime number theorem. So it's a really good place to end. In a class on analytic number theory, we'd probably spend about a week going through all these integrals exactly, and carefully estimating all these things. My feeling is this is more than enough detail. All right, so we didn't get to the virus.